Swayam Prabha. Digital India. Educated India.
Now we'll be seeing the star delta conversion or the transformation. So we'll see the star delta transformation. Okay. So in the case of star delta transformer, we'll be having a some connection which looks like a star. This is also known as the Y connection, because if you invert it or draw like this, okay, so this becomes on Y. So this is basically the Y or star WYE connection, and then we have this also like a star. So 1, 2, 3. So basically just redraw this, so it can be like 1, 2. So R1 is here, R2 is here, and R3 is here. Similarly, R1, R2, and R3. Then we have some other kind of connections. This also can be represented as T. Okay, so same kind of thing. So this and just inverted, and this is T. R1, R2, R3. So this is 1, this is 2, and this is 3. Similarly, we have delta connection. You form the delta. So R1, 2, this is 1, this is 2, this is 3, R3, 1, and R2, 3. Or this can also be represented as an pi network, where a 3 can be taken as a common terminal, and we have 1, 2. So R1, 2 is here. So this is common 3. So this will be R3, 1, and this is R2, 3. Okay. So when we talk about the conversion, it means that the terminal characteristic should be same. In any case, like source we did. So here also the equivalent resistance between the terminal in star should be same as delta. Okay, delta. So suppose between terminal 1 and 2. Okay, so between 1 and 2, if you see in the star, the equivalent resistance is R1 plus R2. Like see from here 1 and 2, because this is not at all connected anywhere, it is floating. So the equivalent resistance is R1 and R2, which should be equal to the equivalent resistance between 1 and 2. So this will be in series parallel with this. So R12 parallel with R23 plus R31. If we solve this, it will be nothing but R12 R23 plus R12 R31 divided by R12 plus R23 plus R31. This is R1 plus R2. So this is equation number 1, for example. Between terminal 2 and 3. So we'll be having as R2 plus R3, and R2 plus R3, and the equivalent from the circuit you can see between 2 and 3. So R12 plus R31 parallel with R23, correct? So, or we can just directly write it as okay. I'll just R23 parallel combination of R12 plus R31. This is clear. So this equation can be taken as 2. So if you solve this, okay, if you solve this combination, you'll get R12 R23 plus R23 R31 divided by R12 plus R23 plus R31. Okay, so in the similar lines, okay, if we try to write, okay, the terminal between 1 and 3, okay, 1 and 3, so that will be R1 plus R3 in the case of a star connection. We can see here between 1 and 3, this is the series connection, this is floating, and that will be equal to 3 parallel with R23 plus R12. So if we solve this, it will be R12 R13 plus R31. If we consider this R31 R13 same, but for the sake of uniformity we can consider this R31 plus R31 R23 divided by R12 plus R23 plus R31. We can give it the equation number 3. For transformation, if we talk about suppose first we do delta to star. Delta to star means given values are in the form of delta, so given in is delta, which is nothing but R12 R23 and R31, and we have to find star or y, which is but nothing but the R1 R2 R3. So clearly if you add all these the terms and then divide by 2, what, so if you do these steps, we'll get R1 plus R2 plus R3 nothing but R12 R23 plus R23 R31 plus R31 R12 divided by R12 plus R23 plus R31. So this can be taken as equation number 4. Now equation 4 minus equation 2, we get R1 here. Okay, so R2 plus R3, this term will get subtracted, so R1 will nothing but the R12 R13 divided by R12 plus R23 plus R31. Now from equation 4, okay, this separate. Now equation 4 minus equation 3, if we do, then we can calculate R2. R2 will be nothing but R2 R3 into R2 R1 divided by R12 plus R23 plus R31. And if we do equation 4 minus equation 1, then we get R3 as R23 R31 divided by R12 plus R23 plus R31. So what we got here, we got all the terms of star R1 R2 R3 in terms of R1 R2 R2 R3 R3 R1, which is delta terms. Okay, so now consider star to delta conversion. Okay, so it means that the given values are in stars. So given quantities are stars, right? R1, R2 and R3, and we have to find out. So this is star and this is delta. We have to find out the delta, right? So R12, R23 and R31. So basically we need to find out R12 in terms of R1, R2 and R3. Okay, so from the equation, this expression, right? Suppose this is given as 5, this expression as 6 and this expression is 7. Okay, so now from 5, 6, 7, if we want to calculate these quantities, okay, so let me write here. So from equation 5, 6 and 7, so calculate R1, R2 plus R2, R3 plus R3, R1. If you calculate this quantity, what you'll get? You'll get R12 square R2, R3, R3, R1 plus R12, R23 square R31 plus R12, R23, R31 square. You can just try it out. This is only one very simple step, and then here you'll get this. So this is the term which you'll get. Now a very simple step, just take the things common. So in this equation, if you want to take R12, R23, R31 common, so we'll be left with R12 plus R23 plus R31, and we have the denominator as 2, 3 plus R31 raised to power 2. This power will get cancelled of this one. So what we'll get? We'll get R1 R2 plus R2 R3 plus R3 R1 is nothing but R1 2 R2 3 R31 divided by R12 R23 R31, which is all sum. Okay, so this equation is number 8. Rewriting equation number 7, which is nothing but R3 as this is nothing but equation 7, right? We have just rewritten this. So now perform action of equation 8 by equation 7. What will get? So equation 9. So we have clearly got R12 in terms of R1 R2 R2 R3 divided by R3. On the similar fashion, if you calculate the other terms, R2 3 and R31. Okay, so if you calculate the R23, which will be nothing but same R1 R2 plus R2 R3 plus R3 R1 divided by R1, and if you calculate the R31, you get the same terms as R2. So we have already seen the ideal voltage and the current source. So if we just recall the ideal voltage source, so that used to be represented by this symbol, or sometimes we'll find the DC voltage represented by this symbol. Okay, so these represent the ideal voltage source. And if you see the current source, so the ideal current source is represented by this symbol. This is ideal current source. We have already discussed these ideal voltage and the current source in the previous lectures, and now we are looking at the what are the practical source is represented. Practical, or we can also say real, or we can say physical source. Okay, so these basically are the source which are in the regular circuits, or the practically which is observed. So they are represented in series with the non-ideality, which is represented as resistance in series with the voltage. So suppose this is a voltage Vs, or similarly here, and the current is I here, Is, which is rated current. Now the non-ideality is taken into consideration by having the internal resistance Rs and the voltage Vs. Rs is the source resistance, which is internal resistance of the voltage source. So this is the representation of a practical voltage source, or real voltage source, whatever you say. Now if you see the non-ideality in the case of current source, you will be finding the resistance which is in the parallel, which is also shunt resistance. So this is practical current source. Rs and the Is, internal resistance. Internal resistance of this, if you see, is 0. Ri is 0. Here the internal impedance is infinity. Okay, so what we want to understand from this real practical sources is that can we transform from one type of source to the another type of source. So this is the purpose today. So before going to that part, let us first draw the characteristic of these two sources. Okay, so we are just trying to find out how the voltage will be varying. So in case of, suppose here we draw, okay, so these are the axes where you can say this is a, okay, so for practical voltage source, the voltage will be constant. So if it is a voltage and here it is current, so it does not depend upon the current. So but if you see here, if the more current, the drop will be more, IR drop will be more, so net voltage will reduce. So this is the practical voltage source, you can see, and I'll just change the color so that you can just differentiate. This is something which is ideal, so red one is ideal, so this one, this is represented here, red, ideal current source, and the blue one is nothing but the real or practical, whatever you say. So this is the voltage current characteristic. Okay, this is a voltage current characteristic. Similarly, if we see the characteristic of a suppose this is your current again, okay, so this is a voltage axis. So here if you write the voltage and here it is suppose current, now the ideal, first we'll draw the ideal characteristic. So let us draw the ideal characteristic. So this is something like ideal characteristic. It will go like this, little, it will just tilt. So now if you'll see, in this case, the terminal voltage at any voltage, the terminal voltage will be same, but the amount of current will be different for the non-idealities. So basically it is reducing. Similarly here, the current can be same, whatever the current you want to draw you can take, but the magnitude of voltage will reduce at different instant depending upon the value of the current. So this is what we just wanted to understand. So now let us see the transformation. From now we'll just talk about the source transformation. So before we go into the detail of transformation, let us understand if there is a source. Okay, so suppose there is some source. For time being, we'll consider, okay, non-ideal source. So this is the non-ideal source, and now it is connected to some part of the circuit. Okay, so this is some black box, which is some big circuit. Okay, big circuit. Now we want to convert, we want to transform it. For the sake of simplicity, for solving the network, I'm just showing, we'll see how we can convert it. Okay, and this is the same circuit, whatever the circuit is, this one, same circuit is this. So in this particular case, suppose this Vs and Rs was the magnitude of voltage and the current resistance here. Similarly, the current is Is and this is Rs. Okay, so we want to convert this voltage source, which is non-ideal voltage source, to this current source. So the whole process of converting this is known as the source transformation. So as you can see that when the circuit will be from the terminal A, B, here also if we mark A, B, the circuit should not see any difference whenever we are changing the source, otherwise the full system will get disturbed. So which means that the terminal characteristic of this and the terminal characteristic of this should be same. So that is most important point of transforming a source into another source. First one, terminal characteristic. Okay, terminal characteristic should be same. So what does it mean? It means that the open circuit voltage VAB should be maintained. And then short circuit current, short ISC, or the short circuit ISC between terminal A and B. Okay, so this ISC is short circuit current which is flowing when the terminal A and B shorted. This also should be maintained. Okay, so these are the two conditions which we have to make sure that followed in both the circuit, this one and this one. If these two conditions are maintained, then for the same circuit we can transform this source into this source between A and B. Okay, now let us see how we are going to do there. So we'll just look into this change or the transformation which is going to happen. So what we'll do, we'll just write the equation of the terminal characteristic in both the cases, and we'll just try to match them. Practical voltage source, right? So this is the practical voltage source. So what is the VOC? We'll take the terminal A and B only. So what is the VAB? So VAB is nothing but, we'll maintain S, and RS in the case of voltage source. Fine. So what is the VAB? The open circuit voltage between the terminal A and B is nothing but Vs. And when A and B is short, so this is for voltage. Now on the other side, this is open circuit voltage. We'll mention that. Okay. Now see the short circuit current. Between terminal A and B shorted. AB shorted. So we have one resistor and then we have ideal voltage source, and this resistance is R and this is Vs. So now the terminal A and B, just short them. When this is short, the current will flow. What is current? IAB or ISC, the short circuit current or the current flowing when A and B shorted, so both are same, is nothing but V by R, Vs by Rs. This is the short circuit current. Now we have to make sure that the terminal characteristic is same, which means that the current should the amount of current which is flowing should be maintained. So and converted to current source equivalent. So this is the thing. This is I and this is R. So when we short this A and B, so now what is the open circuit voltage? In this case, open circuit voltage is nothing but the voltage which is appearing across this, which is nothing but the total current will go into the R. So this is VAB is nothing but I into R in this case. Fine. Now what is the short circuit current? So if we short this AB, now the full current will go into this. If we use this current division rule, or if we see this is a R which is nothing but 0 and the parallel combination of R0 and R is nothing but 0. So in that way we can equivalent resistance can be calculated and we can find that the total current, the I current will be flowing through this. So ISC or IAB is nothing but I. So from 3 and 4. Now you see for equation 1. What is VAB? The open circuit terminal voltage Vs. What is here the VAB? I into R. Okay. So now let us equate and find the voltage. So Vs is equivalent to I into R for transformation, right? And the ISC or IAB is nothing but Vs by R or I. So these two should be same. We have already compared here. So if we have a current source whose magnitude is nothing but I, which is Vs by R, which is nothing but the I which is assumed here, so it is nothing but Vs by R. This is the short circuit current, and now see what will be the voltage. Voltage should be Vs, right? So this has to be Vs means Vs by R into R, so this has to be R. Okay, so this is the R and this is Rs. Okay, so basically the Rs has to be equal to R, and the current has to be Vs by R. So this is the So just let us draw a clear transformation circuit. So we have this voltage source. This is represented or transformed into a current source. Fine. So this is Vs, this is Rs. So this Rs should be equal to this Rs, and the current should be Vs by Rs. This is Is. So this is the transformation, and vice versa. So if the current source is given as I, then Vs by R or ISRS will be the voltage in this particular case, or this is true both ways. Just you have to calculate with the magnitude of voltage in the current source. But the resistance which is coming in series with the voltage source and the parallel with the current source will be same. So that we have seen from here while comparing the equation 3 and 2. This equivalent source. Okay. Now we'll take one example to understand this. So just if we can convert this into a series part. Okay, so just do the equivalent circuit. You can calculate the magnitude. So suppose this is your terminal A and this is your terminal B. Okay, so if you draw the circuit of terminal A and B, so this is A, the current from A, it is going to B. Okay, and it is coming back between A and B with a resistance of, this is B. So this is 5 ohm and this is your 2 milliamps. Now it is very much clear that we have to convert into a voltage source where the resistance will appear in series and the ideal voltage source will appear like this. Now here, why I took this example? Because something interesting is going to happen. What about the polarity? We know that this is 5 ohm, this also will be 5 ohm, and this is 2 milliamp. The voltage will be I into R, so 2 into 5, 10 millivolt. So this voltage will be 10 millivolt, which is how it is calculated. Vs is nothing but the I into Rs. So this is I is your 2 milliamp into the 5 ohm. So it is nothing but 10 millivolt. Now the current is going downward. Okay, so we'll just remove this polarity because we have to learn how the polarity will be decided. So voltage is going downward, the current is flowing from A to B. It means that it will flow in this direction, so this will be positive and this will be negative, right? This current will flow and it will go this way, correct? So voltage drop will be happening across the resistance in direction of current, so this will drop here. So B will be at a positive side and A will be negative side, will be this polarity between A and B. So basically the polarity deciding factor, if you want to decide the polarity, the direction of the current source which is pointing will be resulting as positive in case of voltage source. This is nothing but I. So this is just for remembering the concept of polarity. So whenever the current is flowing and the direction of the current, that terminal will be taken as a positive. So this is AB. If the current is going towards A, then A should be at the high potential. And this is the logic. According to the flow of the direction of the current, we can decide the polarity of the voltage. So currently we have taken the sources which are independent. It means that the magnitude of voltage or the current source is not dependent on the other element or the parameter of the circuit. Now, if the voltage or current source is a dependent source, in that case, we'll see now what is the condition we have to make sure. Okay. So now if we want to have an example, okay, So we'll just see the source transformation. For dependent sources. Okay, so far we have seen the independent source. Now we'll be seeing the source of dependent source. So we can understand this by considering an example. So let us understand let us take one example. Okay, a circuit in which the independent sources are there. So let us consider this is a positive terminal 10 volt. This is the 5 ohm resistor, and assume this as a 4 ohm, and you can have 8 ohm resistor here and 6 ohm, and this is the dependent voltage source whose magnitude is 24I, and I is the current which is flowing in this resistor. So this is I. So this is a current dependent voltage source. So the voltage source whose magnitude is depending upon the current which is flowing in this 5 ohm resistor. So let us first mark it. The main point, suppose we can just change the color. A and B. Okay, and this can be C. So the current which is flowing between A and B, now you'll see. We have to make sure only one thing here. The on which the voltage source or the source is dependent. Should not be disturbed. What does it mean? Okay, so this condition is very clear, but what does it mean? So what we have to make sure that whatever happens to the transformation, the AB terminal should not, the element between A and B terminal, basically the 5 ohm resistor having a dependent quantity I on which this voltage source is dependent, should not be disturbed. So we can have this current I as like this only, and we are not going to change this. We can use this branch. We have to solve this particular branch. Okay, or we can have a different color just to identify that. So this particular branch BC, sorry. Okay, so this BC branch can be converted as usual, keeping this current as an undisturbed. So now if we consider the B and C, so this is nothing but one resistor and one, this is the branch, and this is 6 ohm, and this is nothing but 24I. So if it is a dependent source, consider this is an independent source, so we can aram se understand and apply the earlier laws or the source transformation formula, by which we can have this B and C. So 6 and 4, so 6 ohm will be here, so this also will be 6 ohm only, and the value of this current will be Vs by Rs. So Vs here is 24I by 6, it will be 4I. Okay, so this is the I, this source current is calculated at Vs by Rs, which is nothing but the 24i by 6, which is 4i. This is 4i. So I have made a mistake by representing this. Since it is an independent representation, so we'll not use this representation, we'll be using this. So this is a dependent source which is depending upon the current I which is flowing in this resistor. Now redraw this circuit, and now you see here, so the complete part, this is the only transformation part. This has nothing to do with the final circuit. So we have a voltage source of 10 volt with this polarity, then this is the current I in the 5 ohm resistor, then between B and C we have a current source 4i. You can ask that why this polarity has been taken this way. So if we short B and C, the current will be flowing from positive to negative. It means it will flow in the upward direction. So that's why it is taken as upward. Or by shortcut, the positive terminal should be given the arrow. So this is how the arrow is given towards positive. Now this branch is nothing but the 6 ohm. Okay, and then the remaining circuit 4 ohm, 8 ohm. So this is 4 ohm and this is 8 ohm, 6 ohm, 4i, 10 volt. So this is the circuit. So now this circuit basically converted by using this branch for the independent and the dependent source. Only the difference will be the dependent parameter should not be altered. So this I is still I, which is in the 5 ohm current. So this is the whole meaning of having a source transformation of dependent sources. Now if we want to solve this circuit, suppose we just want to solve this circuit, so let us go little further step, and we can move little top so that circuit is visible. Okay, now so from here we can take this portion, okay, and calculate the series parallel combination 4 and 8 in series. So we have a voltage source, so this part of the circuit will remain same, and the current source also will remain here, and then one resistance which is equivalent resistance will be appearing. So this is R equivalent, this is 5 ohm, and this is nothing but the 4i, and this is 10 volt. Okay, so what is R equivalent here? So R equivalent is nothing but 6 ohm parallel with 4 ohm plus 8 ohm. So this is series, this is the series combination. Okay, so these two are series 12. So if you solve this, it will be nothing but 12 into 6 by 12 plus 6. So this will be 4 ohm. So R equivalent is nothing but the 4 ohm. This is the I which is flowing here. The only condition, as I said, that this should not be changed. So here we can think of like we can transform this source into the current source, and then two current sources will be in the parallel, so we can easily add those two current source or subtract depending upon the current action and solve the circuit. But the condition for transforming this source was this element should not be disturbed. It means that we can only have an option to convert back this source to a voltage source. So let us convert this into a, so this side is free space, so we can draw here. So this is our 5 ohm, this is our 10 volt, this is 5 ohm, and this is the current I, correct, this way, and this polarity will be like this. Okay, and the Vs will be Is into Rs, it means 16I. Okay, this 16I nothing but the Is into Rs, 4I into 4, which is 16I. Now you can see this is simple one loop. Now apply KVL. If you simply apply KVL, so from this point, so you can see the rise in voltage. This is the circuit. So if we apply from this point, so we are rising the voltage 10, then will be drop. How much drop? 5 into I, because IR will be 5 into I, and then the same current will flow in this. So drop again 4 into I, and then again drop of 16I is equal to 0. So if you solve the circuit,